Welcome back to lesson number 12. In this lesson, we're going to be talking about the direct product of groups, something called the internal direct product, or I'm going to demonstrate it as the subgroup product, and then we're going to learn how to identify groups as direct products. Okay, so what we've done in the past is we've taken two groups, G and H, where H is a subgroup of G, and we've identified something called the quotient group, or G mod H. Now, you might ask, when you hear the word quotient, you think division. So you might ask, why don't we define a product group? Well, that's what we're going to try to do today. So if you're given two groups, G and H, you can define the product of G and H. So let's define that. It's a relatively straightforward idea. So let G and H be groups. We want to define the direct product, which is going to be written as G cross H, which is going to equal the set of elements, which are combinations of G and H, where we're going to have G being in G, so for all G in G, and H in H. So you can kind of imagine this just like how you would do a regular cross between any two spaces. Like, let's say you want to describe the plane, or r squared. That's just any two pairs of points where each point is a real number. In this case, G cross H, or G product H, is just any two pairs of group elements where the first one is identified with G and the second one is identified with H. And of course, what comes with the group is a multiplication law. So let's define the multiplication, where G1, H1 dotted with G2, H2 should equal G1, G2, comma, H1, H2. Hopefully that's pretty natural of an idea to make it work that way. In a sense, there's not many ways it could work, because if you think about it, you can't do something like G1, H1 because G and H are just arbitrary groups. You have no idea that it makes sense to multiply group elements between them. So really the only way to define this reasonably is to have the product of the group elements in G here and the product of the group elements in H here. Okay. This is our definition, so now let's prove some more interesting properties about product groups that will give you a better understanding of how they work and maybe why we want to study them. Okay, properties. A lot of these should be relatively straightforward, so I'm going to ask that you try to prove them on your own. It'll be a good exercise. So the first one is, of course, that G cross H is a group. So you have to verify that you have identities, that the multiplication is associative, and that you have inverses. All of which should be relatively straightforward given the definition of a multiplication. The second one is about the size of this group. So the order of G cross H should quite naturally be the order of G times the order of H. Okay. The third property is that if I want to, instead of finding the order of the entire group, if I wanted to find the order of some element, G comma H, this is going to be the least common multiple or lowest common multiple of the order of G and the order of H. This third one we're going to explore a little bit more. And then the fourth property is that you have this thing where certain elements automatically commute. For example, if you took G comma 1 and you multiplied it with 1 comma H, you're going to get the same thing as 1 comma H multiplied by G comma 1. And this is true for all G in G and H in H. So you can think of this as basically like if you set one of the things to the identity, then it commutes, where in this case you set the G element to the identity and H can be anything. This is pretty clear. and this will come up to be more helpful later in this video. So just like convince yourself and maybe write out a proof of, let's say, conditions 1, 2, and 4. And we're going to try to work through condition 3, which is about the order of any element, on our own. We're just going to see kind of what conclusions we can make. Some experimental evidence. So let's start with an example. Let's consider the direct product, which is z mod 5 cross z mod 10. And this is going to be my group G. I'm just going to call it G. So first of all, we see that the order of G has to be equal to 5 times 10, since z mod 5 has order 5 and z mod 10 is order 10. So we get the total size is 50. Okay. Now let's try to find the order of certain elements. Let's say I want to find the order of the element 1, 2. Well, I see that if I have 1, 2, added again, I get 2, 4, 3, 6, 4, 8. Once again, if I add it the 5th time, I'm going to get 5, 10, which is of course equivalent to just 0, 0. Because, well, 5 in z mod 5 is 0, and 10 in z mod 10 is also 0. So the order of this element has to be 5. And if you notice, well, this is just the least common multiple of the order of 1 in z mod 5, which is 5, since 1 times 5 is 5, and the order of 2 in z mod 10, which is also 5, because 2 times 5 is 10. Okay, let's do a slightly different example. The order of 1, 5. Hopefully the answer for these should be relatively intuitive for you, but it's somewhat helpful to try to work it out and find once you hit that 0, 0. So for this one, hopefully you should find that you have to add it 10 times, or the order of the element is 10, because once you add it 10 times, well, you see that if you do it 5 times, you're going to get that this first number gets to be 0, but the second one is not going to be 0, because 5 has order 2. So if you do it 5 times, well, it's going to be, 2 doesn't go into 5, so it's not going to be 0, whereas 1 does have order 5. And we see that in particular, this is the least common multiple of 5 and 2, where 5 is the order of 1 in z mod 5, and 2 is the order of 5 in z mod 10, because 5 plus 5 is 10. So hopefully this fact of getting the order of any element should be relatively clear. In fact, one might hope, in this case, that G is isomorphic to z mod 50, right? Because I got a z mod 5, z mod 10, I'm multiplying that together. It only makes sense if that gives me z mod 50, right? I mean, that's just kind of how numbers work. Unfortunately, this is not true in this case in particular. If you try to find an element of order 50, which would then make it z mod 50, of order 50, you can't. I recommend you try this on your own, but you'll find that no matter what combination of elements you choose in z mod 5 and z mod 10, none of them will get you to order 50. If you can't get order 50, then you can't get z mod 50. So let's try another example where maybe this does work out how we would want it to. Okay. Let's try z mod 2 cross z mod 7. And I'm just going to call this G. So we first see that the size of G is 14, and we might hope that it's z mod 14. In fact, in this case, we do get that G is isomorphic to z mod 14. Let's prove it real quick. Well, we see that the element 1, 1 in G has order 14. Well, why is this? Well, we get that the order of 1, 1 equals the LCM of the order of 1 in Z mod 2, which is 2, and the order of 1 in Z mod 7, which is 7. And we know that 2 and 7 are what's called relatively prime, so they share no prime factors, which means the LCM of 2 and 7 is 14. Okay. So now let's try to kind of generalize this idea and prove a nice result when it comes to these direct products. So the theorem is going to be, if we have Z mod M and we're producting it with Z mod N, then this is going to be isomorphic to Z mod M times N if and only if M and N are relatively prime. Relatively prime. Let's prove this. And just to note for our examples, it works when M is 2, N is 7, then we get 14. But we saw with 5 and 10 it doesn't work, but you might notice that 5 and 10 are not relatively prime. They share the prime factor 5. So according to our examples, this holds. So let's do the first direction, which is first we're going to assume that M and N are relatively prime, and then prove that these two groups are isomorphic to each other. So assume M and N are relatively prime. Then we find that the element 1, 1 in Z mod M cross Z mod N is going to have order M times N. Has order Mn because, well, the LCM of M and N has to equal Mn. This is because that's just the definition of the LCM when M and N are relatively prime. We should just note quickly that the LCM is actually, it has an equation for it. It's M times N over the greatest common denominator of M and N. So the LCM is actually always less than or equal to Mn, and it's only equal when the GCD is 1, and the GCD being 1 is equivalent to M and N being relatively prime. Now note that the order is this number because M is the order of 1 in Z mod M, and N is the order of 1 in Z mod N. Okay, so since this element has order Mn, it generates the whole group, so it's equal to Z mod Mn. Okay, the other direction, which is we're going to now assume that these two groups are isomorphic to each other, and then we're going to prove that the things are relatively prime. So assume that Z mod Mn is isomorphic to Z mod M cross Z mod N. So let's let psi be an isomorphism between these two groups. Of these groups. Okay. So we know, since just by the definition of Z mod Mn, there exists some element G in Z mod Mn such that the order of G is, well, Mn. There has to be some element that generates the whole group. In particular, we think of that element as 1, because 1 plus 1 plus 1 all the way to Mn, then you get to 0. So now we notice that what if I took psi of G? And so I looked at psi of G in Z mod M cross Z mod N. Note that I'm letting this isomorphism go from Z mod Mn to Z mod M cross Z mod N. Of course, if you define it the other way, you could do something like psi inverse. It's easier if we think of it this way, though. So let's try to find the order of this element. Well, we see that psi of g to the LCM of m comma n has to equal 0, or the identity in z mod m cross z mod n. Why is this the case? Well, you can kind of just think of this logically. I mean, if, let's say, psi of g looks something like k comma r, where k and r are some integers, then if you're doing it to the order, like if you're doing it to the power of LCM n comma n, then you're going to get something that looks like LCM m comma n times k comma LCM m comma n times r. But of course, the least common multiple of m and n, well, m goes into that and n goes into that. So this has to be equal to 0, 0, because this part is 0 and this part is 0, regardless of what k and r are. Which means that this property means that the LCM of m comma n has to be greater than or equal to the order of psi of g. Right? Because let's say you had psi of g, which is order 10 or something, and then you found that like psi of g to the 20 was 0. Well, the order of an element is the lowest number such that the power of it to that power is 0. So if we find something gets sent to 0 by this power, it has to be greater than or equal to the order. But we know that the order of psi of g is just equal to the order of g. This is a property we proved when talking about isomorphisms and homomorphisms. And the order of g is equal to m times n. So we get the LCM of m and n is greater than or equal to mn. But if you remember, we discussed before that by the definition of LCM, it has to also be less than or equal to m times n. But you might realize that this then implies exactly what we want, which is that the LCM is equal to m times n, which implies that m and n are relatively prime. Okay. And that proves exactly what we wanted. So now you know if you take the product of any two cyclic groups, like z mod m and z mod n, you have a good idea of what it looks like if you know that m and n are relatively prime. If they're not, it has a slightly different structure to it. That's a little bit weirder. So we usually like to think of these direct products when they are relatively prime. It's also a great way of breaking down direct products, or breaking down groups. For example, if you had a cyclic group of, let's say, like 12, you could rewrite this as z mod 3 cross z mod 4, because 3 and 4 are relatively prime. And maybe it might be that thinking of z mod 12 as this is easier than thinking of it as this. So hopefully this should beg the question, when can we factor groups into products? In some ways, factor groups into products. So in this case, z mod 12, we could factor, in quotations, it into z mod 3 cross z mod 4. Now, if you remember when we were studying quotient groups, we used the first isomorphism theorem, which told us a way of finding isomorphism between g mod the kernel of phi to the image of phi, or psi, whatever function you want to use. And so that gave us a way of identifying quotient groups as something. What we're going to try to do now is try to identify groups as products. So try to find a way of factoring a group into a product. So to do so, we're going to need to study another kind of product, which I'm going to call the subgroup product. Okay. So take two subgroups, H and K, which are some subgroups of a group G. The subgroup product which is in some senses understood as the internal direct product under certain conditions, is the set HK, which equals all those elements H times K for all H in H and K in K, which is hopefully pretty natural. So it's the set that looks like, just taking any H here, any K here, and multiplying them together. Now, hopefully you should notice, this is not necessarily a subgroup. HK is not necessarily a subgroup. A subgroup of G. Why is this? Well, if you do H1K1 times H2K2, there's no reason you should immediately assume that you can kind of move those H's over to make it look like HK. So we have to impose some extra assumptions on these subgroups to make sure we get something that's useful to study. Any random set is kind of boring. Once it has a property like a multiplication on it that makes it into a subgroup, we can study it using group theory. So let's try to make some assumptions on these subgroups. So we'll prove a quick lemma, which is if H and K commute with one another, commute in G, then HK is a subgroup of G. Okay, let's prove this. It's pretty straightforward. So if I take H1K1, which is an HK, and multiply by another element, H2K2, I see if H and K commute, I get this is equal to H1H2 times K1K2. Remember, because if they commute, I can swap any two elements. So I can just move them around until it looks like this, but clearly this is an HK. So this tells me that HK is closed under multiplication. So we've gotten that's closed under mult. Now we need to check that it's non-empty, or that 1 is in the subgroup, but clearly 1 is in H, 1 is in K, so I get that the identity is in HK. Okay. Now I need to show you have inverses. Well, if I have HK, then I can multiply by H inverse K inverse, and since they commute, this is just equal to H inverse times K inverse, which is of course just equal to 1 times 1, which is just the identity. So I have inverses as well. So I have all the properties needed to make this a subgroup. Now that we know it's a subgroup, let's try to find even more things about it. So you might be curious, like, how big is this? What is the size of HK? It's not immediately obvious, assuming, of course, that it's a subgroup. So let's prove that. Theorem. Of course, from now on, I'm assuming that HK is a subgroup. This theorem says that the order of HK is going to be the order of H times the order of K divided by the order of H intersect K. Let's prove this. So we're going to prove this. Hopefully this might remind you of orbit stabilizer. I have the order of something over here, and I have the order of another thing divided by something. So that kind of reminds you of the size of the orbit equals the size of the group divided by the size of the stabilizer. So let's let H be a group action on G mod K. Where I get that, my group action says H dot GK, where this is a left coset in G mod K, is just going to be equal to HGK. So just like left multiplication. So I find that if I want to find, let's say, the orbit of just K, the subgroup K, is going to look like all those elements HK for all H and H. Right? Because the orbit is just where everything gets sent, and so if you multiply by H everywhere, you're just going to get HK. But we can rewrite this as the left cosets of our subgroup HK. Because, all these elements are H times K, and if I take a coset of that, the left coset, well, that's just going to be HK, little k times the big subgroup K, which is just going to be little h times the big subgroup K. Okay. Now let's find the stabilizer. I see that the stabilizer of K is going to be equal to those H and H such that HK equals K. Of course, when HK equals K, well, it just means that H has to be in K, right? So this is just equal to H intersect K. All those elements of H that are also in K. Thus, by orbit stabilizer, I get that the order of H divided by the order of the stabilizer, which is H intersect K, has to equal the size of the orbit, which is HK, or the order of HK, divided by the order of K. Remember, because it's HK mod K. And now I can simplify this by multiplying by K on both sides, and I get that the order of HK equals order of H times order of K divided by order of H intersect K, as desired. Okay. So what this tells me is if I have that H intersect K is just the identity, or if it just has size 1, then I get the size of HK equals the size of H times the size of K, which is the size of H cross K. I also get that, well, if the size of HK equals the size of G, then HK equals G. So hopefully you should get an idea now of some of the assumptions we want to make to try to find a way of rewriting this subgroup product as a direct product and thus writing the group as a direct product. Okay. So to figure this out, or to get a better motivation for it, let's just look at a general product G cross H. Be a general product of groups. So we automatically have two subgroups. We have the subgroup, which I'm going to call G prime, which is going to be equal to the elements G comma 1 for all G and G. And then we have the subgroup H prime, which is going to be equal to all those elements 1 comma H for all H and H. We see that, well, we first get that G prime and H prime commute, as we showed at the beginning. So this tells me that G prime, the subgroup product G prime H prime, is a subgroup of G, or G cross H, I should say. For the second condition, if I get that G and H don't intersect, so this is just the empty set, This is generally true because we're just saying G and H are just two random groups. Of course, this might be different if G and H are subgroups, or one is a subgroup of another. But if we get this, then we get that G prime intersect H prime is just the identity. 1, 1. And so, this tells me that G prime H prime is going to have the same size and is actually going to be equal to my direct product, G prime cross H prime. And finally, I have that for all elements G comma H and G cross H, I get that I can write GH as a product of G prime and H prime. GH equals G comma 1 times 1 comma H, where this is in G prime and this is in H prime. This tells me that G prime H prime has to equal G cross H, which means that, well, it's also equal to G prime cross H prime, or isomorphic to, I should say. Okay, so this is what I get in general direct products. This is what I should hope to see. So if that's the case, let's try to generalize this to any group and see if we can find a way to factor it. So let's generalize. Given a group G, if you have subgroups H and K, such that the following things hold, we're going to have a direct product. So the first one is that H and K commute. This guarantees me that the direct product, the subgroup product is actual subgroup. The second one is that H intersect K is just going to be the identity. This tells me that the size of the subgroup product is the size of the direct product of H and K. And 3, if I get that for all elements G and G, I get that there exists unique elements H and H and K such that G equals HK. So this tells me that I can take any element in G and write it as HK. Then G is going to equal HK, the subgroup product, which is isomorphic to H cross K. And so I can factor it as such, H cross K. So you might notice that conditions 1 and 3 are relatively challenging to prove. And in practice, it might be kind of hard to demonstrate. Luckily, if we assume 2, with assumption 2, or criteria 2, we can prove the others with relative ease using another condition. There is an easier condition. Since in practice it's relatively hard to demonstrate that two subgroups commute, and you can write any element in the group uniquely as a product of them. So let's try to demonstrate that. And the way we're going to show it is using normal subgroups. So we're basically going to assume that H and K are normal in G. So if H intersect K is just the identity, that's condition 2, and H and K are normal, then I get that H and K commute. Let's prove this. So we see we're first going to define something called the commutator. So for all h and h and k, define h comma k in these brackets to be h times k times h inverse times k inverse. So you see that if hk equals 1, then h and k commute. Okay, well, if that's the case, let's see what happens. Let's see if we can prove that h and k have to be 1. So, since k is normal in G, I get that hk, which equals hk h inverse times k inverse, well, hk h inverse has to be in k, by definition, since k is normal. So I have something in k times k inverse, so I get that hk is also in k, since it's just two elements in k multiplied by each other. But similarly, since h is normal in G, the commutator h comma k equals h, and then in parentheses k h inverse k inverse. But since h is normal, this k h inverse k inverse is also in h. So I get something in h times another thing in h, which means my commutator is also in h. Thus we've shown that the commutator is both in h and in k, so it's in h intersect k. But h intersect k is only the identity, so this implies that h comma k has to equal 1. So it is in fact the identity, and thus h and k commute. Now we want to try to prove the other condition can also be satisfied, which is, writing an element uniquely by h times k. So, theorem, if h intersect k is just the identity, and I get that the order of G equals the order of h times the order of k, then and of course I assume that h and k are normal in G, then I'm going to get that, of course, as we wanted, for all G and G, there exists a unique H and H and K, such that G equals HK. Okay, let's prove this. So we first want to show, if HK equals 1, then H equals K equals 1. Okay. Well, we see that if HK equals 1, then we get that H equals K inverse and K equals H inverse. Well, remember that groups or subgroups contain inverses of their elements. So if H is K inverse, well then H has to be in K. And if K is H inverse, then K has to be in H. Which means that H and K are in both H intersect K, because they're both in H and both in K. But H intersect K is just the identity, which means that H has to equal K, has to equal the identity. Okay. Now we can continue. So let's let G equal H1K1 and H2K2, and we're going to try to prove if this is the case, then H1 equals H2 and K1 equals K2, which means it can be written uniquely. So we get that this implies that H1 K1 times times K2 inverse H2 inverse, because we're multiplying by the inverses on the right, so I get that K2 inverse H2 inverse is the identity. Well, since H and K are normal and their intersection is just the identity, we proved in the previous theorem that that implies that they commute with one another. So I'm going to swap these elements around till I get H1 H2 inverse times K1 K2 inverse is the identity. But remember, we just proved that if something in H times something in K is the identity, then H1 H2 inverse is the identity, and K1 K2 inverse is the identity. And of course, this implies that H1 equals H2 and K1 equals K2, as desired. So finally, we get the best way of identifying factorizations, which is the following theorem. If G is a group with two normal subgroups, H and K, normal in G, such that we get the following. We get that H intersect K is just 1, or it's just the identity. We also get that the size of G equals the size of H times the size of K. Then G is isomorphic to H cross K. And just for a quick proof, you should try this one on your own. But just to, it's pretty straightforward what you have to do. But you just want to define an isomorphism which sends H comma K to HK. And you'll see that this will work. It will become an isomorphism between these two groups and prove that G is isomorphic to H cross K. And so hopefully you noticed that this idea of normality played a huge role in quotient groups. And it once again played a huge role here as well with products. So it happens to be that normal subgroups are kind of this great way of breaking down larger subgroups into smaller ones and factoring them in some cases. Okay, so let's end off with some exercises. So for the first exercise, I want you to let the order of a group G equal P times Q, where P and Q are primes and P is less than Q. I want you to determine when G is isomorphic to Z mod P cross Z mod Q. And you might have to use the CELO theorems. And then the second exercise is if G is isomorphic to G prime and H is isomorphic to H prime, I want you to prove that G cross H is isomorphic to G prime cross H prime. On top of that, I want you to find a counterexample to the converse of this. So find a counterexample to disprove the converse, to disprove the converse, which says if G cross H is isomorphic to G prime cross H prime, then G is isomorphic to G prime and H is isomorphic to H prime. And maybe as a hint, think about some of the theorems we proved at the beginning of this video lesson about cyclic groups and their products. Okay, thanks for watching.